Okay, let's unpack this. We're diving deep today into some of the biggest questions humans have ever asked, really, just by looking up at the night sky.
Hmm.
That feeling makes you wonder, what does it all mean? How does this whole universe thing work? And where exactly do I fit into this cosmic picture?
That impulse, that curiosity, it feels fundamental, doesn't it? And, it seems like there's a real appetite for science right now. You see it everywhere.
Yeah, in movies, books, streaming shows, trying to make these big ideas, accessible.
Exactly.
Yeah.
Which is great for what we're doing here. We're drawing from excerpts of Astrophysics for People in a Hurry.
Yeah.
It's just a fantastic, concise guide.
Really lays out the core ideas, the big discoveries shaping how we see the universe now.
So our goal today is to walk you through this material, pull out the absolute key insights, maybe some surprising bits, and give you a solid grounding in modern astrophysics.
Like a fluency almost, so you can connect with those headlines and really get what they mean. Hopefully spark some, aha moments.
Yeah, that's the plan.
Okay, so where else to start but the very, very beginning? The sources call it maybe the greatest story ever told.
The origin of our universe, yeah. Nearly 14 billion years ago.
And starting from a speck, a volume less than 1/trillionth the size of a period. It's just wild.
It's almost impossible to picture. And in those first moments, we're talking trillions, then millions of a second. The universe was, it was this incredibly hot, dense, seething soup.
Right, not just any soup. You've got these fundamental bits, quarks, leptons, bosons.
And they're antimatter twins.
Swirling around.
Constantly being created from energy, annihilating back into energy, following Einstein's ENCA.
That two-way street, energy to matter, matter back to energy. It shows just how much energy is packed into even tiny amounts of mass.
Okay, but here's the kicker from the source material. For anything, anything to exist today, galaxies, us, there couldn't have been a perfect balance, right?
Exactly. Perfect symmetry would have meant total annihilation, nothing left but light. The crucial thing, the source's stress, was this tiny imbalance. Like 1,000,000,001 matter particles for every billion antimatter particles.
That tiny fraction, that one extra particle per billion, that's everything. That's why we're here. Matter just barely won that cosmic war.
Wow. So, okay, a millionth of a second in, things cool a bit, quarks start sticking together.
Forming protons and neutrons hadrons. And by about a second, electrons kind of freeze out of the energy soup, roughly one electron for every proton.
So you've got this hot, dense plasma expanding, cooling for hundreds of thousands of years.
And then, a key moment around 380,000 years after the Big Bang, the temperature drops below about 3,000 Kelvin.
What happens then?
Well, those free-flying electrons, they finally slow down enough to get captured by the nuclei. They combine.
Forming the first stable atoms, mostly hydrogen and helium?
Overwhelmingly, yes. And this is critical. Because the electrons weren't free anymore, they stopped scattering the photons, the light particles.
So the light that was trapped in the soup could finally escape.
Exactly. It was suddenly free to travel across the universe. And that light released 380,000 years in.
That's the cosmic microwave background, like the universe's baby picture.
Precisely. That faint afterglow we can still detect today. It's amazing.
Okay, so the Big Bang gives us hydrogen, helium, the light stuff. But what about, us? The carbon, the oxygen, the iron?
Yeah, for that you need something else. The sources call it stellar alchemy. The universe needed kitchens.
Kitchens.
Cosmic kitchens. To cook heavier elements.
And those kitchens are the cores of massive stars.
You got it. Through thermonuclear fusion, they smash hydrogen and helium together to make heavier things. Carbon, oxygen, silicon, all the way up to iron.
But those elements are stuck inside the star, right? How do they get out?
Well, the really high-mass stars, they don't go quietly. They end their lives in massive supernova explosions.
Right.
And that boom is powerful enough to blast all those newly forged elements out into space, enriching the surrounding gas clouds.
And that's how you get the material for new stars, new solar systems,
Yeah.
systems like ours with rocky planets.
Exactly. Clouds rich enough in heavy elements to form planets capable of complex chemistry. And that brings us to carbon.
The MVP of elements for life.
Pretty much. Its ability to bond in so many ways is just fundamental for the complexity we see in life on Earth. It forms more compounds than everything else combined.
Our own little corner had a rough start, though. Bombardment, impacts.
Included the big one, 65 million years ago. Wiped out the dinosaurs.
Which, ironically, cleared the stage for mammals.
Yeah, allowed mammals to diversify, eventually leading to, creatures like us who can sit here and talk about it.
The sources touch on that before the beginning question, too. What was there before the Big Bang?
It's the ultimate question, maybe, but scientifically. Our physics, our understanding kind of breaks down at that initial point, that singularity.
So we can't really probe before with current science.
But not empirically, no.
Yeah.
Not yet, anyway. And, some people see that gap and say, that's where you need a prime mover, some external cause.
But the scientific approach is more acknowledging ignorance.
Precisely. Ignorance isn't failure. It's the frontier. It's where we look next. And there are ideas out there, quantum mechanics, string theory, multiverse concepts, simulation ideas.
Very speculative stuff, though.
Very. But they're attempts to grapple with it scientifically.
But the big takeaway about where we came from chemically
Is that connection. Every atom in your body. The hydrogen, the carbon, the oxygen, the iron. It's traceable.
back to the Big Bang for the light stuff.
And back to the fiery hearts and explosive deaths of ancient stars for the heavier stuff.
We are literally stardust given life. That's pretty profound.
It really is. A direct chemical link to the cosmos.
So moving on from what we're made of to the rules of the game. The universal laws. This was a huge shift in thinking, right? Realizing the heavens and earth follow the same rules.
Absolutely massive. That was Newton's genius. Connecting a falling apple to the moon's orbit. Same force. Gravity.
Before him, it was like, earthly stuff is messy, heavenly stuff is perfect and unknowable.
Pretty much. Divine rules up there, mundane rules down here. Yeah. Newton showed it's all one system, one set of physical laws. Universality.
And this idea caught on fast, especially with light, using prisms.
Yeah, spectroscopy. When scientists split sunlight into its spectrum, its barcode of colors,
They found
the exact same chemical fingerprints, the same barcodes as elements here on Earth. Hydrogen, iron, calcium, right there in the sun.
mind-blowing at the time, I bet. Physics works 93 million miles away, just like it does in the lab.
It was revolutionary. And it led to finding helium on the sun first. Remember that story?
Oh, yeah. Named after Helios, the sun god, because they thought it only existed there, founded decades later on Earth.
The only element discovered off-world first. And then there was nebulium.
Ah, the mystery element in nebulae.
Yeah, this strange spectral line nobody recognized. Turned out, just ordinary oxygen.
But doing weird things because space is so empty.
Exactly. Conditions were different, super low density, but the fundamental physics of oxygen, unchanged. The laws held. Universal.
And this applies to constants, too, like the speed of light. It's the same everywhere, and it's a limit.
Seems to be. As far as we can tell, these fundamental constants are truly constant. And yeah, the speed of light, C isn't just a suggestion. It's baked into relativity. Nothing with mass gets there.
It's not like saying, oh, humans will never fly. That was just a lack of tech. This is different.
Fundamentally different. Breaking C would mean breaking physics as we understand it. Physics that's been incredibly well tested.
The sources have that great little anecdote about whipped cream, too.
Yes. Being told, oh no, whipped cream always sinks in hot chocolate here. It's just not true.
Because physics, density, buoyancy.
Right. Whipped cream is less dense, so it floats. Doesn't matter what the local custom or belief is. Physics doesn't care about opinions.
Which is kind of comforting, in a way. Objective reality.
Definitely. It's consistent.
So these universal laws also explain shapes. Why are big things in space planets, stars generally round?
It comes down to gravity again. Once an object gets massive enough, gravity dominates. It pulls everything equally towards the center of mass.
So the most efficient way to pack everything in close is a sphere.
Exactly. Like how surface tension makes tiny water droplets spherical. Gravity does the same for planets and stars. It overcomes the material's own strength.
Even mountains are just tiny wrinkles on a planetary scale.
Oh yeah. Shrink Earth down to a billiard ball, and it'd be smoother than any actual cue ball. Gravity just smooths things out on that scale.
But smaller things like asteroids or Mars's moons, they can be lumpy.
Because their gravity is weaker. The chemical bonds holding the rock together are strong enough to resist gravity's pull and maintain those irregular potato shapes. Size is key for roundness.
And a rotation messes with the perfect sphere, too. Makes things bulge.
Right. Spinning throws material outwards at the equator, causes an equatorial bulge, a flattening at the poles, an oblate spheroid. Earth is slightly like that.
But Saturn is the really obvious one.
Yeah, it spins fast, mostly gas. Very noticeable bulge, you can see it flatten. Extreme cases, like pulsars spinning hundreds of times a second, get seriously distorted.
Okay, extending roundness outwards. The observable universe is described as a sphere. That's a different kind of sphere, though, isn't it?
Totally different. It's not a physical wall, it's an information horizon. It's defined by the distance of size. Light has had time to travel to us since the Big Bang, considering the universe is expanding.
Because things far away are moving away faster due to expansion.
Right. And there's a point, a distance, where the expansion of space itself carries objects away from us faster than the speed of light.
So light from beyond that distance can never reach us. The space stretches too fast.
You got it. It's a horizon of observability for us. Like the horizon at sea, it's a limit to your view, not an edge of the world. It's defined by light speed and the age and expansion of the universe.
Makes sense. Okay, shifting to how we actually see all this. Our eyes are so limited. Visible light is just a tiny sliver.
A realization that started simply. William Herschel, 1800, splitting sunlight with a prism, putting thermometers in the colors.
And finding heat beyond the red light he could see.
Infrared, below red. And a year later, Ritter finds something beyond violet using chemicals. Ultraviolet.
Suddenly, visible light is just one part of this huge electromagnetic spectrum. Radio waves, microwaves, X-rays.
Gamma rays. And astronomers initially were kind of slow to build telescopes for this invisible light. They were used to optical.
But you need those other bands to see different things, right? Cold gas, black holes.
Absolutely. You need the whole spectrum for a complete picture. Cold gas glows and radio waves. Dusty, star-forming regions in infrared, violent stuff in X-rays and gamma rays.
Which brings us to radio astronomy's accidental start. Bell Labs, phone static.
Carl Jansky, trying to track down interference for phone calls, builds this rotating antenna, finds this faint hiss.
That peaked on a sidereal day lined up with the stars, not the sun.
He realized it was coming from the Milky Way center. Cosmic radio waves. Just amazing. Found by accident.
And then Grote Reber, the amateur, builds a dish in his backyard.
Inspired by Jansky. Confirms it, makes the first radio maps, basically pioneers the whole field. Incredible story.
And now we have these monster telescopes. Huge single dishes like FAST in China, or arrays like the VLA.
The Very Large Array, yeah. Or the VLBA, spread across the U.S. for incredible sharpness. Linking dishes together gives you amazing resolution.
And LMA, up high in the Chilean desert, for microwaves.
Yeah, the Atacama Large Millimeter Submillimeter Array needs to be high and dry because water vapor in our atmosphere blocks those wavelengths. It lets us peer into those cold, dusty cocoons where stars and planets are being born, stuff invisible to optical telescopes.
Plus X-rays, gamma rays, even weird stuff like gamma rays from thunderclouds here on Earth.
Terrestrial gamma ray flashes, yeah.
It's wild.
But the point is, by using instruments across the whole spectrum, we get this multi-wavelength view. It's like giving ourselves cosmic superpowers. Each window reveals different physics, different objects.
Really drives home how much is out there beyond what our eyes can detect.
For sure.
All right, let's dive into the deep end now. The big cosmic mysteries. Dark matter and dark energy. Starting with the space between galaxies. Billions of galaxies, yes, but what's in the void?
It's not totally empty. You've got dwarf galaxies, for one. They actually outnumber the big guys like Andromeda or the Milky Way, but they're faint, hard to see.
Often getting shredded by bigger galaxies, too.
Yeah, galactic cannibalism. And then there's intergalactic gas, really hot gas, mostly hydrogen and helium, filling the space in galaxy clusters. It glows in X-rays.
And that gas actually outweighs the stars in the galaxies.
By a lot, yeah. Maybe 10 times more mass in that hot gas than in all of the stars of cluster galaxies combined. Plus, maybe some rogue stars flung out, isolated supernovas.
But even adding all that up,
Yeah.
it still doesn't explain how galaxies rotate.
Yeah.
Like the missing mass problem.
Exactly. That's where dark matter comes in. Vera Rubin's work in the 70s was pivotal, looking at spiral galaxies.
You'd expect stars way out on the edges to orbit slower, like Pluto around the sun.
Based on the gravity from just the visible stuff, stars, gas, dust, yes, they should slow down. But they don't.
They orbit way too fast, almost as fast as stars closer in.
Which implies there's a huge amount of unseen mass providing extra gravity, holding those outer stars in their orbits. This led to the idea of vast, invisible dark matter halos surrounding galaxies.
And this isn't just like dim stars or black holes we haven't found. Ordinary matter that's just hard to see.
The evidence strongly suggests no. Things like the amount of deuterium and helium forged in the Big Bang, plus tiny details in the cosmic microwave background, they constrain how much ordinary matter, protons, neutrons, can exist.
And it's not enough to account for that missing gravity.
Not even close. The discrepancy is about 6-to-1 universe-wide, so dark matter has to be something else, something exotic.
Something that interacts mainly through gravity, doesn't really mess with light.
That's the picture. It's dark because it doesn't emit, absorb, or reflect light. It just gravitates. A strange, invisible cosmic component. It dominates on large scales, galaxies, and clusters, but here on Earth, its effect is totally negligible.
And it was crucial early on for making structures.
Absolutely essential. In the early universe, gravity from ordinary matter alone wasn't strong enough to overcome the expansion and clump together fast enough to form the galaxies and clusters we see. Dark matter provided the extra gravitational scaffolding needed to get structure formation going.
Okay, so that's the mystery mass, dark matter. But then there's dark energy. Even weirder.
Oh yeah, way weirder. Dark energy isn't mass, it's pressure. A mysterious pressure inherent in the vacuum of space itself,
Acting like anti-gravity, pushing things apart.
and causing the expansion of the universe to speed up, to accelerate. That was the big shock.
This ties back to Einstein and his cosmological constant, lambda.
It does. He put lambda in his equations originally to keep the universe static, which everyone assumed it was. When Hubble found it was expanding, Einstein supposedly called lambda his biggest blunder.
But the math allowed for it as an energy density of empty space.
Exactly, a property of the vacuum itself that would create a repulsive force. It was mathematically possible, just seemed unnecessary once expansion was found. Until
1998, distant supernovae.
two teams, independently studying Type Ia supernovae, these great standardizable candles found they were dimmer, and therefore farther away, than they should be if expansion was constant or slowing down.
Meaning the expansion must have sped up over time.
Bingo. The universe is accelerating. And the best explanation, that repulsive force from empty space, Einstein's lambda, resurrected, they needed a name.
Dark energy.
Dark energy, because it's unseen and we don't know what it is, but it dominates the universe's energy budget.
And the numbers are just staggering. What's the breakdown again?
The latest estimates, dark energy is about 68% of the total mass energy content of the universe. Dark matter is around 27%.
Leaving 5% for everything else. All the stars, planets, gas, dust, us.
Just 5%. Everything we directly observe and interact with is just a tiny sliver of cosmic reality.
That's incredibly humbling. And the theory behind dark energy is shaky.
Well, the mismatch between the theoretical prediction for vacuum energy from quantum physics and the actual measured value of lambda is astronomical, doesn't even begin to cover it.
The 10 to the 120 factor.
Yeah, 1 followed by 120 zeros. It's arguably the biggest disagreement between theory and observation in the history of science. It screams that we're missing something absolutely fundamental about gravity or quantum mechanics or both.
So we know it's doing something accelerating the universe, but we have almost no clue what it is.
That's about the size of it. And because it's a property of space itself, as space expands, there's more of it, leading to more acceleration, runaway expansion.
Meaning distant galaxies will eventually recede faster than light and disappear from our view?
Effectively, yes. Carried away by the expanding space between us. A universe increasingly empty and accelerating away from us. It's a strange cosmic destiny.
Definitely food for thought. Okay, let's pull back towards home. Our solar system, not quite as empty as we might think.
Not at all. Interplanetary space is buzzing. Gust, rocks, ice particles, the solar wind streaming out from the sun, magnetic fields. Earth plows through tons of meteoroids every day, mostly tiny stuff burning up as shooting stars.
But there are bigger chunks left over too. Asteroids, comets, from places like the Kuiper Belt.
Right, and that brings up Jupiter's role. Its huge gravity acts like a cosmic goalie, or a burly big brother, as the sources put it.
Deflecting comets from the outer solar system, protecting the inner planets.
Seems likely. It probably deflected or captured many potentially hazardous impactors, giving Earth longer periods of stability, which might have been crucial for complex life to evolve undisturbed.
We use that gravity too, though, for spacecraft.
Gravity assists, slingshotting probes like Cassini around planets to gain speed and change direction, essential for exploring the outer solar system efficiently.
And the moons. So many moons. Over 200 now.
And counting. Loads of fascinating ones. Eo's volcanoes, Europa's hidden ocean.
A top spot to look for life beyond Earth.
Absolutely. And Pluto and Charon locked in their orbital dance. Plus Uranus's moons, all named after literary characters.
Bit quirky. We also get the aurora thanks to the solar wind hitting our magnetic field.
Yep, particles channeled down to the poles, exciting atoms in the atmosphere. Beautiful displays on Earth. Even more spectacular on Jupiter and Saturn with their stronger fields.
Okay, looking back at Earth, what can you actually see from space?
From orbit. City lights at night are obvious if you know where to look. Big weather systems, smoke from large fires. Maybe some human-made boundaries like agricultural patterns, but famous structures like the Great Wall. Nope, too narrow.
And from further out, the moon, Mars.
From the moon, Earth is this stunning blue marble. Clouds swirling, but no sign of cities or life, really. From Mars, maybe continents, ice caps with a good telescope, but from Neptune,
The pale blue dot.
that iconic Voyager image. Earth is just a single pixel, almost lost in the sun's glare. Really puts things in perspective.
So if aliens were looking for us, how would they find us? Just seeing Earth wouldn't be enough.
Probably not just by visible light. We're not that special visually, but our technology, that's another story.
We're loud.
In radio waves and microwaves, incredibly loud. TV broadcasts, radar, radio signals, they leak into space, making Earth a conspicuously artificial radio source compared to natural background noise.
Like how Jocelyn Bell first thought pulsars might be little green men. Their signals were so artificial looking.
Exactly, LGM-1. It shows how encountering something truly unexpected forces you to consider all possibilities, even aliens, before settling on a natural explanation.
But beyond technology, could they detect life itself using chemistry?
That's the idea behind searching for biomarkers in exoplanet atmospheres, using spectroscopy, looking for chemical fingerprints of life.
Not necessarily intelligent life, just biology happening.
Right. Some molecules, like water or CO2, aren't definitive, but finding lots of free oxygen, that's a big one.
Because oxygen is reactive, it gets used up quickly. Something needs to be constantly making it.
Like photosynthesis does on Earth. Finding abundant free oxygen in an exoplanet's atmosphere would be a very strong hint of life as we know it.
Methane is another possibility, maybe? Though it has non-life sources, too.
True. And the sources also mention, somewhat darkly, that maybe signs of industrial pollution smog, certain acids could be biomarkers for the absence of intelligent, sustainable life. A sobering thought.
But the sheer number of exoplanets being found, thousands confirmed, estimates of billions of Earth-like worlds in our galaxy.
It makes the search feel much more hopeful, doesn't it? It shifts the question from if life exists elsewhere to where and how we can find it. The potential is immense.
Okay, let's bring it all together, this cosmic perspective. The sources say it's sublime, interesting, useful. It expands our minds, humbles us.
Absolutely. That feeling of connection, of understanding even a little bit of this vastness, it's powerful.
But there's a potential downside acknowledged, too, that the sheer scale can make Earth's problems seem insignificant, make us forget poverty, conflict, environmental issues.
It's real tension. The universe's indifference can feel liberating, letting go of ego, but it could also maybe lead to apathy if you're not careful.
The book uses that analogy of an adult looking at a child's problems, spilled milk, broken toy seeming trivial, suggesting maybe humanity's conflicts based on borders or beliefs look similarly immature from a cosmic viewpoint.
It definitely challenges our tendency to put ourselves at the center of everything, which astronomy has constantly chipped away at. Our tribe, our nation, our planet. Maybe not the be-all and end-all.
Imagine if everyone really felt that perspective. Would borders matter as much? Would we see our shared humanity on this one small planet more clearly?
It's a nice thought. There's that story about the psychologist feeling crushed and insignificant after a planetarium show zooming out to the edge of the observable universe.
But the author contrasts that, feeling energized, connected, precisely because humans can figure this stuff out. Our brains evolved to understand the cosmos.
Which suggests the perspective isn't inherently depressing. It maybe depends on how much ego you brought into it in the first place.
The sources offer some great ego softeners, too, the molecule comparisons.
Oh, yeah. More water molecules in a single glass than glasses of water in all the oceans.
Sure.
Meaning you've definitely drunk water that passed through, I don't know, dinosaurs, Genghis Khan, everyone.
And more air molecules in one breath than total breaths in the atmosphere. You're breathing air that was breathed by Newton, by your ancestors.
It connects us physically, chemically, through time and space. And the stars. More stars than grains of sand on all Earth's beaches. More stars than seconds since Earth formed. More stars than words ever spoken.
Yeah, those really hit home. Puts the ego in check.
For sure.
And looking out is looking back in time. Seeing cosmic history unfold because light takes time to reach us.
Reinforcing that kinship again. We're chemically related to the stars. And maybe even biologically. If life hopped from Mars to Earth early on the panspermia idea, it challenges our sense of uniqueness.
Which fits that whole history of astronomical demotion, doesn't it? Earth isn't central, the sun isn't special, our galaxy is one of billions. The multiverse idea is just the latest step.
Exactly. So the cosmic perspective, as the sources frame it, cultivates humility, maybe a non-religious spirituality, an appreciation for scales large and small, open-mindedness.
But not so open your brain falls out.
Right. Seeing beauty in the physical laws, not just the objects. transcending our immediate needs, questioning our symbols, embracing kinship on multiple levels.
It's more than just facts. It's about shaping a worldview.
And the drive to explore, to keep learning about the cosmos. It's not just fun, though it is. It's presented as almost necessary.
To prevent us sliding back into self-centered views that breed prejudice and conflict.
Yeah. Staying connected to that bigger picture is vital for a forward-thinking, maybe even a surviving civilization. A visionary culture needs that cosmic perspective.
So we've covered a lot today, drawing from the sources. From the Big Bang and Stardust to universal laws, the mysteries of dark matter and energy, our solar system neighborhood, the search for life, and finally, what it all might mean for us.
Yeah, the goal was to give you that foundational fluency, those key insights from the material so you can connect the dots next time you see a headline about black holes or exoplanets.
Okay, so as we wrap up this deep dive, here's a final thought, echoing the spirit of the sources. What cosmic truths are still out there, waiting to be discovered? And how might finding them utterly transform life back here on Pale Blue Dot? The journey continues.